So in this lecture, I want to continue our discussion about the Endo Rule. So just to recap, the Endo Rule says that in general, the Diels-Alder reaction, where the dienophile is oriented with its stuff, and I use that stuff, that's my word, with its stuff oriented with its stuff underneath, or a better word is endo, to the forming ring, will occur faster. So this is actually an expansion of the definition that I provided last time, because I'm including a more specific discussion as to what's so great about endo orientation. That is, that Diels-Alder reaction will occur faster. That is to say that, let me just summarize this, endo products form faster than exo products. Endo products form faster than exo products. And so if we had a Diels-Alder reaction where we had our stuff oriented endo, or what we put as left in this sort of two-dimensional representation of the transition state for the reaction, that would form a product like this. And we would say that's fast because we get the endo product. Now, I haven't picked a good example because it turns out that this, in this case, this is the same as the exo product. But let's go ahead and add a situation where that matters. We can do that by simply adding groups to the diene. So let's put the two groups for the diene here plus our alkene with stuff. And we'll look at specific stuff in the next few examples. Well, now here, let's go ahead and consider the 3D perspective. My methyl group's pointing out in a way because both of the alkenes are trans, or E. And then here's my dienophile with the stuff oriented underneath the ring that's forming, which I can show by these dashed red lines. That then allows us to see the difference between the endo product, which is formed faster than the exo product. Okay, so here's my endo product where everything is a dash in this orientation. Plus, I mean, it looks like there's a plane of symmetry, assuming our stuff is the same. But I'm going to go ahead and write this. If we have the dienophile coming in on top, it's not how I typically like to draw my Diels-Alder reactions. But that would just be the enantiomer, or where everything is flipped. Now, again, if the stuff is the same, I guess we have a meso compound again. But we've got either all wedges and all dashes, and these are the endo products. That is, products following the endo rule where the dienophile is oriented underneath, where its stuff is positioned underneath the growing ring, and we then have formation of an endo product more quickly. So the exo product forms more slowly. Now, what do they look like? Well, what we do is we just flip our Diels-Alder dienophile around. Now, the diene stays the same. I don't need a plus here because that's just going to convolute things. But everybody likes drawing the exo transition state. It's just easier to draw. Now, if we have our connection points here, we can do our Diels-Alder reaction. like this. And now our stuff is pointing out, excuse me, out away from the forming ring, whereas our methyl groups in this case are still in their same position. If we want to think about where the stuff is when we unfold and unpack the ring, what we're doing is we're lifting that flap up to give us a structure that looks like this. Now the stuff is going to be attached as wedges. Before that didn't matter, because before we just had this structure and this structure, both wedges or both dashes, they were the same. But here now I've got my methyl groups. Okay, I've got my methyl groups dashed. And so we would say that this is one enantiomer of the exo diastereomer, where we flipped some but not all of the stereocenters from our previous example. So we could consider either the dienophile coming from the bottom, which is what I like to do, or it coming from the top. Both of these are considered to be exo products because for the transition state, the stuff would just be outside of the forming ring. Okay, so these exodiastereomers, if I could take this out a little bit, these exodiastereomers differ from the endo products. Now, again, the reason why I know that the endo products compared to the exo products are diastereomers, because if you compare the exo products to the endo products start off as all dashes. And if you flip everything, you get to enantiomers. But if you only flip some things, you get to diastereomers. Now let's look at the exo product. Okay, the methyl groups are either both the same, but then the stuff is flipped. I'll highlight that in red. Or the methyl groups have flipped, but the stuff has stayed the same. My point is, in the exo products, we flip some of the wedges to dashes and some of the dashes to wedges, but not everything. And as a result, we can't say they're enantiomers. Enantiomers is everything. Diastereomers is some, but not all. If it's none that are being flipped, then they're just the same molecule. Okay, so the exodiastereomers are shown there. Now that's a good important point to characterize, that the exo products are often diastereomers of endo products. And exo products form more slowly than endo products. And that's the nature of the Endo Rule. Said another way, the endo products form more quickly. Now we're talking about speed, slow, fast forming products. That has to do with kinetics. If you recall, when we're studying chemical reactions, we think about thermodynamics, which is the relative stability of two things, how close you are with a bowling ball on the shelf or the floor. Okay, so we've got the thermodynamics, how close you are to the floor, versus kinetics, which is how fast the reaction is going. So what I want to emphasize here is that when we're talking about an endo product versus an exo product, we would say the endo product is the kinetic product. The endo product is the kinetic product. Now, what's the kinetic product? Well, that is the product that forms the most, forms the fastest. Now, alternatively, and a bit more rigorously, it's more appropriate to say this is the product with the lower activation energy. Product with the lower activation energy. Okay. So that's just us thinking about energy diagrams again. And so if we have a lower activation energy, there's a lower barrier for us to travel through to get onto the products, okay? Said another way, it's the one that forms most quickly. Now what's unusual, and I have to emphasize unusual and uncommon, is that we could also describe the thermodynamic product of a reaction, but in the Diels-Alder reaction, it's typically the case that the kinetic product and the thermodynamic product are not the same. Let's go into this. So the thermodynamic product this is the most stable product that could form in a reaction. It is often the case, like most of the time, the thing that's most stable is going to be the one that's most quickly formed. That is to say, and I can't emphasize this enough, most of the time in a chemical reaction, A goes to B, that product is going to be the kinetic product, the one that's most quickly formed, and the thermodynamic product, the product that's most stable. The Diels-Alder reaction is unusual. In a Diels-Alder reaction, the thermodynamic product is often the exo product. Well, that's unusual because the exo product is not the kinetic product, but it's not unexpected. If we look at our approach to making the product, let's look at this product that we try to draw, and let's consider, so I'm going to consider the exo product again. So if I have stuff pointing out and away or exiting the forming ring, I'm drawing the exo product. Got this? This is kind of like a transition state, showing you how things form at the peak of the activation energy on an energy diagram. Now, if we draw this product is not that big a deal to draw, right? It's probably cumbersome to draw all of these perspective drawings, but the stuff is pointing out and away. It's not like clumped up compared to our endo product. If you recall our endo product, and maybe you're like, oh man, we have to draw this again, this endo product. And in fact, I'm not only guessing that you're saying that, I know you're saying that. I can hear you. Sorry, it's got a little creepy there. Okay, anyway, back to this. So we have our hydrogen sticking out and our stuff sticking underneath the forming ring system. And we could draw our red lines showing the connection points. Then it gets really bad when we're trying to draw this unfolded, that is the structure that hasn't yet relaxed. And we have to try to fit the word stuff back here. Okay, the hydrogens are sticking out and away. The stuff is sticking underneath. What I want you to recognize is that the stuff now is imposing steric hindrance on the product. We have our stuff on the same side of the ring as the methyl groups. And so there's a steric interaction, we would say. Whereas in the previous case, the stuff is pointed away from the methyl group. We have no steric, I'll call it steric clash. Obviously, these things will relax, but even when they relax, we still have things on the same side. The point is, the energy difference might be not too far away, but the endo product is a lot more difficult in terms of stability to kind of hold on to. It's pushing things a little bit closer together that don't want to be together. And so we get to something that's typically not as stable. It just would be better if things were spread out a little bit more. So no steric clash, and this is more stable. That's typically the case. If you've got something that reduces steric clash and increases stability in the product, then the corresponding transition state, which is at the peak of the activation energy, is typically lower. So it's unusual then that the kinetic product is the more sterically hindered final product. Okay, that's unusual. So it is unusual. So steric interaction, I'll just say unstable. It is unusual that the kinetic product is not the same as the thermodynamic product. And we could actually consider this as an energy diagram for the Diels-Alder reaction. Now what I want to do is I'm going to consider a valley in the middle of my page that is a starting material. And so if you recall, we have like an x-axis that's going to be reaction coordinate and a y-axis that will be energy. Now, if I go over to here, the starting material to the product, I'm going to put endo over to the right, and I'm going to put exo, and I'm going to let exo be lower, exo on the left. Now, the way this looks is forming the endo product has an activation area and a transition state. The top of the hill is our transition state for endo. So this is just kind of reviewing energy diagrams. We have a valley going to a valley by way of a hill. The peak of the hill is the transition state towards the product. And we're going downhill to the endo product that is exothermic, but it's not as exothermic as the exo product. The exo product is lower in energy. So is lower, i.e. more stable. But even though the exo is lower and is more stable, the hill to get to the exo is higher. So this is our TS exo. And that's higher than the endo product. So we say exo is lower, more stable, but the TS endo is faster. So it's formed more quickly. So it's formed more quickly. And that's where we see that if it's formed more quickly, it's the kinetic product. But if it's more stable, as is the case with the exo product, it's the thermodynamic product. Okay. I can't emphasize enough that is not common. Most of the reactions we study, the thermodynamic product and the kinetic product are the same. It's just the thermodynamics is separate from kinetics. Okay, they're related, certainly, but we typically, I think it's most healthy for us to keep them in separate kind of compartments as we're studying chemistry that we bring together readily. But we start by keeping them separated, where we think about speed and stability as being separate from each other, because it allows us to recognize subtleties like this. Now, what I want to do just to wrap things up is to talk about why the endo product is the way it is. So why is what? It's not really a why. It's like how. No, let's just go ahead with a why. Why does the endo product form more quickly or form faster? That's a really good question. Unfortunately, it's kind of vague a little bit. I'm sorry, but it turns out that the electrons from substituents on the diene, substituents, UNs on the dienophile, got that wrong, dienophile. Electrons from substituents on the dienophile can interact with the diene pi bonds, diene pi bonds, to stabilize the transition state. This has a broad term that I'm going to leave vague. It's just something you could look more deeply into if you're interested. This is called secondary orbital overlap. Secondary orbital overlap. It's not as clean as like typical orbital overlap drawings that I like to include. And I mean, we could almost argue that those are not that clean. Now, this works particularly well, works very well with substituents having pi bonds. Okay, let's go through some examples. Now, what I'm trying to do with these examples is I want to show you some endo products. Now, let's consider a case where this matters. We're going to have these two methyl groups here, and I'm going to let these react. Looks like I need to make a new page, sorry. I'm going to let these react with a bunch of different dienes, where we have exo and we have endo. And we have methyl groups going down in this case. That just allows the exo and the endo to matter. I'm going to have my exo be a wedge and my endo be a dash. This follows the general stereochemical model with the endo rule. Now, if you've got a situation where you've got a methyl group and a, let's just start simple. If you've got a methyl group and a hydrogen, the endo product will position the methyl group underneath the forming ring. This is consistent with what we talked about. Methyl is endo. But if we've got a pi bond with in competition for the methyl group, and we do a Diels-Alder reaction with the Endo rule using the exact same diene. Here's our methyl groups. Now it turns out the methyl group is going to be exo, and the carbonyl is going to be endo. So this diene will this dienophile will reorient itself to become endo because it has a CO double bond, which is just another pi bond. So the same thing goes with carbon-carbon double bonds. If we consider this type of species that can react in a Diels-Alder reaction following the Endo rule. So we have our methyl groups from our diene, but then we have our phenyl group, our benzene substituent, pointed down so that this becomes endo. So I've provided two examples of dienophiles that have pi electrons in them, pi bonds, double bonds of some sort. And when the dienophile approaches the diene, it's going to reorient itself to position those substituents underneath the forming ring. It will do so over a typical carbon substituent that doesn't have these double bonds. Now you might say, well, the stuff is more stuffy. It's big when we have that carbonyl in that first example, and when we have that benzene ring in the second example. So isn't it just that it's bigger? No, it's actually about the electrons on the substituents. I could have put a cyclohexane If you want me to, I could draw a system that has a cyclohexane and a benzene ring. And this cyclohexane is actually bigger because it forms a chair structure and has more hydrogens. And I would say this is still going to orient itself so that it's endo. You might say, well, wait, you haven't drawn them that way. You haven't drawn them where the benzene ring is on the left. What I'm doing is trying to illustrate that the dienophile will rotate on itself so that it can adopt something that puts that benzene ring endo. And that's still following the endo rule, we would say. It's a little bit more clear when everything is hydrogen. Okay, this is a big molecule, but this becomes the endo product in this case. Okay, so it's something to keep in mind. I think we've just got a little bit more to talk about in the Diels-Alder reaction. Just some last minute kind of logistical things. Then maybe, well, we'll see. We'll see. Hopefully that wraps up I just got to see what's in the last lecture. Okay, anyway, I'll see you next time.